Hello everyone. So, this is lecture 2 for the module 4. In this lecture I am going to talk about the cache mapping function, full associative mapping, SAT associative mapping, and in the rest of the lecture I will talk about the cache replacement algorithms. When all the cache lines are filled and the new block from main memory as to transfer from main memory to the cache memory, then how to remove the existing cache line, what is the policy. So, for that the cache replacement algorithms are there. In the previous lecture I talked about the direct mapping, one mapping from main memory to the cache memory. So, let us revise this direct mapping and then try to understand why we need other mappings or what are the problems exist with the direct mapping. So, to do this I am taking one example. So, in this example you can see the few datas are given. One is the cache size is given and the size is data. You know that cache memory contains the data part which from the main memory, along with the tag is also stored to identify the data in the cache line appropriately, and along with some additional bits are also there, but so far one is the data part, one is a tag part. Usually tag part is not included in the size when we in general we talk about, unless it is not specified, but the total size of the cache is including the tag bits plus the any additional bits required to design the memory. So, the total memory includes the data plus the additional bits which require to design the cache. So, here the main memory address is 32 bit and memory is a byte addressable. So, memory addressability is a byte addressable and size of the address generated by the processor is 32 bit. Block size or line size is 64 bytes, memory is byte addressable. So, in a direct mapping, processor generated address is divided into 3 parts. One part is word offset, line offset or line, and third part is tag. So, these 32 bit has to be logically divided into 3 parts to identify the data in the cache memory. So, word offset 64 bits. So, 2 is I can write 2 power 6. So, 2 power 6 means uniquely identify a individual byte in this block is 6 bits are required for that. From the 6 bit I can make 64 combinations and individual byte can be addressed. Then in line part, how many lines are there? So, 8 KB data is there, 64 is the line size, then 8 KB divided by 64, this will give me 8 KB means I can write it 2 power 13 divide by 64 means 2 power 6. So, it will give me 2 raised to the power 7 means 128 total lines are there. So, 128 line means I need 7 bits for the line addressing to identify a line. Then what is the remaining bits are there? So, remaining bits for the address will be 32 minus 7 plus 6. So, 32 minus 13. So, how much it is left? It's 19. So, 19 bits for the tag. So, this is the address splitter for the direct mapping. Now, if I want to calculate the total size of the cache memory, then I have to add this tag bits as well. So, each line will contain total 19 bits tag bits and the 64 byte memory. So, 64 byte data part. So, 64 into 8 that bits. So, 64 into 8. So, these many bits multiply with how many lines? 2 raised to the power 7 lines. So, that calculation you will do, you will get the total number of bits in cache memory. In cache memory, CM stand for the cache memory. So, if you have to calculate the total size of the cache, then you have to add the tag bits and the data part and then multiply with the total number of lines. So, this is the direct mapping. Now, what is the problem with the direct mapping? Problem in the sense the mapping is straightforward. So, mapping function is very simple, but performance wise what is the problem? So, for that let us take a simple example to understand where the problem is there and then what can be the better solution for this. So, to devise a better solution, first we look at the problem and then try to see what is the solution for that. So, let us assume I have cache memory which contains 4 lines and line index number are 00, 01, 10 and 11. 4 lines are there, so that is why 2 bits are sufficient. And let us say main memory addresses are generated by the processor. So, address generated are, I am saying the block number or line number. So, the main memory block number addresses. So, block number let us say 0, then 1, then 4, then 5, then 8. Well, let us say these are the addresses which are generated. These are block addresses. So, processor will generate one of the address, one of the word address that belongs to these blocks. So, 0 as per the direct mapping, the 0th block will map to, I am writing here, to the line 0. Block number 1, second address is for the block number 1. So, block number 1 will map to the second line, and then block number 4 will map to here. So, there already block 0 is there in this line because the mapping is fixed in the direct mapping. So, that is why I do not have any other choice to put this block number 4 to any other line. Even these 2 lines are empty currently, but I have to put as per the mapping criteria to put this B4 into the first line only. So, I have to remove this. So, the utilization, cache utilization here you can see is less. Even lines are empty, but still I have to remove the data. Removing data, what are the implication can be there of removing the data? If I am removing means maybe in next reference processor will require the same data. Let us say here after 8 it is 0 is required then. So, idea should be like that until I have the lines empty, I should have first fill the empty lines, and removing should be done only after all the lines, cache lines are filled. So, now how to do this? Similarly, same thing can happen for let us say B1. So, after B4 the next block is which is reference, that is 5. So, 5 is mapped here. So, that is why I have to remove 5 even the 2 lines are empty. So, this is the native problem with the direct mapping. So, how to overcome this problem? Why this problem is coming? Due to the fixed mapping. The source of the problem is fixed mapping. Fixed mapping of what? Block, main memory block to the cache line. So, if we can remove this fixed mapping and I say that okay, any cache line, any block of the main memory can map to the any cache line or can be there in any cache line, that this problem will be solved. So, the solution to the problem is that if I can devise a mapping function such that no line replacement until a line is empty in the cache memory. So, for that I want to say that it is that any block of main memory can map to any line of the cache memory. If this can be achieved, then this problem can be solved. So, now in this picture you can see that one block of main memory pointed here, this can go in any line of the cache memory wherever the line is empty. There is no fixed mapping from block to cache line, and that will solve the problem of the cache utilization or the poor cache utilization. So, this kind of mapping is called as fully associative mapping. It is, in general, it is called as associative mapping, but to specify or differentiate between the next mapping that we will do after this fully associative, we use the word fully associative. Complete associative means any line can go, or any block of the main memory can go to any line in the cache memory. So, what is fully associative mapping now? The main memory block can load in any line of the cache memory. Main memory address is now interpreted into two parts. One is tag and one is a word offset. You can write word or word offset. And this tag is uniquely identifies the block of the main memory. So, now let us look how this fully associative mapping is done and how the address split up will be there. So, for that let us take one example. In this example, the cache memory size is given 2k words of the data, means it can accommodate 2k words of data from the main memory, and the main memory is 64k words. It is a hypothetical memory system. Usually the main memory size is very large in today's computer. Block size is, let us say, 4 words, and memory is a word addressable. So, the number of address bits is decided from the main memory size. Main memory size is 64k words. So, 64k words means 2 raised to the power 16. K means 2 power 10, 64 means 6. So, 2 raised to the power 16 is total words. To uniquely identify these 16 words, I need a 16-bit address. So, this is a 16-bit address. Now, how this address will be logically divided to get the data from the cache memory, because processor, we know processor generate address as per the main memory. As far as the processor is concerned, processor is not aware of the cache memory. There is a basic Newman model has not been disturbed. So, 4 word is a line size. So, first I have to, so here address split up will be in 2 parts. One part is word offset and other part is the tag. So, word offset 60 word is 4 words, block size is a 4 words. So, within a block, to identify a single word I need 2 bits. From the 2 bits I can identify, let us say, first word from 00, second word from 01, third word from 10, and fourth word address can be 11. So, accordingly a unique word can be identified from the block or from the cache line, which can store the 4 words. Remaining bit will be tag bits. What is the remaining bit? 16 minus 2, so that is a 14 bits for the tag. So, that is the address split up. So, if you write some addresses, let us say some memory addresses I am writing. So, let us say 1, 2, 3, 4, this I am writing in hexadecimal. So, each digit in hexadecimal represents the 4 binary bits. So, 1 will be represented with 1, and 2 will be 0010, 3 will be 0011, 4 will be 0100. So, now out of these 16-bit address, first 14-bit will be treated as a tag that will be stored along with the cache line, and this address is the first word from the block which is transferred from the main memory, and block address is this much. Complete block address is this. So, you can say these tag bits will be unique for each block of data. So, now we understood how to split the address into 2 parts. One is word offset and then the other is a tag for the fully associative mapping. Now, let us see how the word is located or the address generated by the processor. For that, the data is located in the cache. What is the associative circuitry is required to identify the word from the cache memory. So, you can see here, this is the memory address generated by the processor. Tag and word, logically it is divided as per the size of the cache memory and the main memory, and in the cache memory you can see each line contains 4 words, or because that is the block size or line size. So, here it is shown in vertical. 4 words are there, word number 1, 2, 3 and 4 in each line, 1, 2, 3 and 4 in each line. Now, for any given address, to check whether it is there in the cache memory or not, how to find it? Because for each block of data, the tag is unique, that we can see from the, if you write the sequence of 16 bits starting from 0 0 all zeros to the maximum 2 power 16 minus 1, that sequence you will write, you will see that after every 4 addresses the leftmost 14 bits combination is changing. That means the tag bits for that particular example which I discussed in the previous slide. So, the tag bits is different for each block. So, means, and as per the associative mapping, any block of data can be reside in any cache line, whichever is empty I can put in any line. So, that is why I have to check whether the data is available in the cache, the requested data by the processor is available in the cache memory or not. I have to compare all the tags, all lines tags from the cache memory. So, that is why all line tags are compared with the tag of the address generated by the processor. So, here you can see all tags, there is a circuitry which is required that can compare all these tags. So, the number of lines of 1000 lines are there, the 1000 comparisons will be there, 1000 tags has to be compared. So, it is a complex task, the circuitry becomes a complex. So, rest of the operation is same. If this tag is compared, any of the lines tag, then I say that this word is available in the cache, and then the respective word can be transferred with the help of the tag bits comparison to the processor. That word can be transferred to the processor, and if it is not available, it is no tag compared with the tag of the address generated by the processor. In that case, that word has to be taken from the main memory, it has to simultaneously transfer from the main memory to the cache as well as to provide to the processor. So, here one problem is solved, that now any block of the main memory can map to the any cache line. So, one problem is solved, but what is the other problem here? This comparison. This is the complex. The circuitry becomes complex, cost will increase, delay will also be there because the digital circuit, so some delay is also associated for each comparison. And we know that due to this time only we do this cache memory business. We introduce the cache memory in between the processor and the main memory due to this time lag only, that is because there is a huge difference in terms of the processor speed and the memory access time, main memory access time. So, to overcome or to reduce this gap, we introduce this cache memory, but this gap will further it will be reduced to reduce the number of comparisons. So, in the direct mapping, the fixed block to cache line mapping is there. In fully associative mapping, so there in direct mapping I have to compare only one tag, because line to block mapping is there. So, directly that line can be checked whether this line contains the requested address or data or not. If it is not, so there only one line mapping is required, one tag is to be compared, but here the number of tags are equal to the number of lines in the cache. So, that is another extreme. So, can we reduce this number of comparisons, and still we say that okay, some liberty is there in terms of putting the data from the main memory to the cache memory. We have some liberty, some flexibility that says that okay, we can put the mapping is not exactly fixed, let us say one line to one block, it can be in some set of lines I can do. So, a new type of mapping is developed or designed that called as a set associative mapping. So, in the set associative mapping, the cache lines are divided into some number of sets. Let us say I have 16 lines, for example, 16 cached lines are there. So, for the 16 cached lines, I say I divide into group of 4 groups, each group contains 4 lines. So, I have 4 sets are there, and within the set I am giving the flexibility, says that okay, within the set whatever the blocks are mapping, they can go to the any of the line within the set. So, you can say the flexibility or freedom of moving a main memory block to the cache memory is restricted to a set. If I say this set is only one set, all the cache line forms only one set, then it will be a fully associative. If the set size is reduced from full all lines to some number of lines, then I say it is a set associative. So, this freedom can be controlled by deciding the or by coming up to the appropriate set size. So, you can devise a mapping function that is in between the direct mapping and the fully associative mapping. So, for example, a given block maps to any line in a given set, and the set size is let us say 2 lines per set. So, that is called as a two-way set associative mapping, and out of these 2 lines, this is 2 lines, this is line 0 and this is line 1. Out of these 2 lines, and this I am calling as a set, one set. So, now some set of blocks, some blocks of main memory will map to this set as per the mapping function. Now, within the line, which line they will go, which set, which block will go to which line, that is not fixed. It depends upon whichever is free in which that block can be transferred. So, that liberty is there. If you increase the set size, that liberty will increase, and the extreme point is you say okay, only one set is there. So, then it becomes a fully associative. So, now let us look at how this address split up will be there with the same example which I took for explaining the fully associative mapping. So, in case of the two-way set associative mapping, how the mapping function will change and our address split up will change. So, memory characteristics or sizes are same, address size will 16 only, here also 16 bit, because memory is 64K and is a word addressable. So, here address will be split up into 3 parts: word offset, new field will come, that is a set offset I can say, and third is no doubt tag. So, out of 16 bits address, word offset will be, because in one block 4 words are there, to uniquely identify a individual word in the block I need 2 bits. Now, what about the set offset? So, first I have to calculate how many sets are there. So, cache memory size is 2K, 2K means 2 power 11 words, 2 power 11 words divide by the 2 power 2 blocks or lines. So, this will give me 2 raised to the power 9 lines. Now, these are total lines, each, because a two-way set associative, so each set contains 2 lines. So, number of set means I have to divide by 2. So, number of set will be 2 raised to the power 8, means 256 sets are there. So, 2 raised to the power 8 means I need 8 bits to uniquely identify a one set, starting from 0 0 0 all 8 bits 0 to 1 1 1. So, now how many bits are left? 8 plus 2 10, total 16 bit address. So, 6 bit for the tag. So, this is the address split up for the set two-way set associative mapping. So, now the mapping will be from main memory block to the set, and within the set in any line, that block can go in any line, depends upon the availability of the line, whether this line is free means there is no block of the main memory is currently reside in that line. Okay. If I make it from two-way set associative to 4-way set associative, let us say, what does it mean? Each set contains 4 lines. So, the flexibility of putting the data from the main memory to the cache is little bit increase from 2 to 4. So, now how the address will be changed? You can easily figure out how. Now, at the time of calculating the sets, so total 2 power 9 lines are there. I say now you divide these 2 power 2 because you have 4 line set. So that will give me 2 raised to the power 7 sets. And now set bit will be 7 for this 4 way, set bit from 8 it will become 7, and the tag bit will from 6 it becomes 5. So no, it is not 5, it is 7, because one bit decrease from here, so that bit will be added to the tag bit. So it will become 7 plus 1 14 plus 2 16. So total 16 bits are there. So like that you can now you can calculate himself for 8 way associativity. Eight-way associativity means each set contains 8 lines. So how many total lines are there? Total lines in the cache are 2 raised to the power 9. So out of these 2 raised to the power 9, if you are making a set of 8 lines per set, so the number of sets will be decreased, and accordingly your address split up will be there. So to understand how the processor generated data will process generated address is interpreted, and whether the data which is required by the processor correspond to that address is available in the cache or not. So to understand this mechanism, we can see in this diagram. So here I took, in place of any fixed associativity, let us say 2 way or 4 way or 8 way, I say it is a k way associativity. K value can be 2, 4, 8, 16. So the number of sets in each set, I have k lines are there, f0, f1 to fk minus 1. Total k lines are there. Now the mapping will be from block to set. So whatever address generated, logically it will be divided into word, set and tag, and from set bits, set to block to this set mapping is there. So it will directly go to that particular set. In that set, in this case, let us say k lines are there. If my k value equals to 4, then 4 lines are there. So the 4 line tag has to be compared only in place of comparing the all lines tags in the case of the fully associative memory. So here the number of comparisons are reduced, and flexibility is also there. So it is better than direct mapping, and in terms of the cache utilization, and compared to the fully associative mapping, performance wise or cache utilization wise, set associative mapping is not as good as the fully associative mapping. But the drawback of the fully associative mapping is this comparative circuit is complex. So the complexity of the circuit is reduced in the set associative mapping, and it is better than direct mapping also. So I can say that k way set associative mapping is usually preferred by the designers for organizing or designing the cache memory, because in general the main memory size is huge, number of lines or number of blocks are huge, and then the comparator circuit becomes a very complex. So that is why by dividing into the sets, that complexity can be reduced and still you are giving the flexibility. So that is the advantage which we are getting. So what we understood that direct mapping, it is set associative mapping is better than direct mapping in terms of the cache utilization, and in terms of the complexity of the circuitry which is required to locate the contents in the cache memory, it is better than the fully associativity. Now come to the cache replacement. When we require the replacement, when all the cache lines are filled, let us say in a fully associative or set associative mapping, at one point of time, let us say all the cache lines will be filled, because for example in a fully associative you can keep any line in the any block of the main memory, you can put in the any line in the cache. So well, all lines have the valid data, and a new block is to be bring from the main memory to the cache, we need to replace one of the existing line. Now how to decide the victim, which line should be removed? For that we use the replacement algorithms. What are the common replacement algorithms? Least frequently used, least recently used, and first in first out, and the random policy. So, let us look at one by one. In case of the direct mapping, there is no replacement algorithm is applicable, because here the mapping is from main memory block to the cache line is a fixed. So, you do not have any choice. The new block is mapped to some particular line. If this line is empty, then you can put directly, but if this line is not empty, you have to remove the existing. Remove means you can overwrite the contents. You do not have any other choice, irrespective other lines are free. So, as far as the direct memory is concerned, no replacement is applicable, but for associative and the fully associative, set associative and the fully associative, these replacement algorithms are applicable. In case of the set associativity, the choice is, the replacement line choice is within the set only. Within the set, let us say it is a 4-way set associativity, then 4 lines are there. So, out of 4 lines any line can be removed. If all 4 lines are filled and new block is mapped to the one of the to this particular set, then any of the line from this can be removed as per the algorithm whatever. So, in case of the least recently used, the oldest referenced block is removed. In the set associativity, it will be the oldest referenced block within the set. You cannot go across the set. In case of the fully associativity, any line from the cache memory can be removed which is referenced by the processor long back or the oldest reference. So, the idea behind, what is the rationale behind this? Rationale is that because that line is now currently in current time frame, it is not going to be used. It long back it is used. So, maybe the block was transferred some time back and it is used completely by the processor, means whatever the program execution related to that has been done, and now it is not required. So, that is the rationale behind that. Second is first in first out, simple. Replace, it says that replace the block that has been in the cache since the longest time, based on the base of when it was come into the cache memory. The block which came first, remove first. Implementation simple, you have to maintain a queue only. What about the implementation of the LRU? Say for example, in case of the 2-way set associativity, you have in each set you have 2 lines are there, LRU you have to implement. So, every time you have to say that okay, which is the least recently used. So, 1 bit is sufficient that can be used to identify which line is the least recently. So, whenever a block is referenced, whenever you put any block into the any of the line, the corresponding line bit you can set, and that set bit means setting 1. That indicates this is the line is, or this is the line which is recently used, most recently used. So, other line you can remove, other line will definitely least recently compared to that. So, implementing LRU in the 2-way set associative is a straightforward. Third is the least frequently used. The block which has had the fewest hits. Hits means the data which is processor generate the address and that corresponding data is found in the cache memory. So, let us say process generate address 2 times 3 times. So, for that particular data hit will be 2 or 3 hits, 4 hits like that. So, for each data like that, the hit can be calculated. So, on the base of the hit we decide which is the least hit, least frequently hit. So, the data which is least frequently hit, that data if I have to remove to put the new, to accommodate the new data, then that data can be, or that line can be rewritten with the new data. Last is the random. Random means without following any algorithm, because to implement any algorithm, let us say LRU or FIFO or LFU, you need some additional computation, you need some additional hardware as well as it will take some time in terms of the computation. So, if you want to go away all these things, then the random algorithm says that any randomly you pick it, but the chances, what is the problem with that? The problem is, suppose you remove the line to accommodate the new block, and that block, the data belongs to that block which you have removed, may be required in the next reference of the processor. So LRU, FIFO, LFU, they have some rationals in terms of okay, whether it's a least recently used or least frequently used, or the data come at, in case of the FIFO, the data came long back. So up to this time this data has been already utilized, so now there is no use of that data, it is time to bring the new data in place of that. In case of random, you are randomly picking, so maybe you are picking a data which is maybe required in the next few references. So in that case, that data will be, once it is referenced, then you have to take from the main memory, and then the penalty will be there, taking from the main memory. So in this picture, let us look at the how the associativity variation over the cache memory size. Cache memory size here in terms of the data which cache memory can accommodate. And the y axis, the heat ratio is shown. Heat ratio indicates that the amount of references which found in the cache memory, an amount of references generated by the processor found in the cache memory, and x axis says the size of the cache memory. So here cache memory size is increasing from 1K, 2K to up to the 1M. So you can see here direct mapping is inferior in all the cases. Whatever the size of the main memory is there is always inferior compared to other mappings. And when the size is small, let us say it is up to the 2K, then 4-way, 8-way and 16-way mappings are performance wise almost same, and here performance criteria is the amount of references which are available in the cache memory. And if you move from, let us say, from 4K size, from 4K cache memory size to up to 16K, then you can see the significance difference in terms of the hit ratio between the associativity 4-way, 8-way and 16-way. And once size is sufficient, here you can say is a 1 megabyte of memory, means a huge memory is, may compare to the cache memory size, it is a large huge memory is there, then the effect of these associativity is on on the hit ratio is negligible in comparison to 2-way, 4-way, 8-way and 16-way. Means the cache memory is sufficiently enough to accommodate the data from the main memory to execute the program. In the most of the time the references are available in the cache memory only. So here you can see the hit ratio is almost at this level is near to 0.9, means 90% of references are available in the cache. So from this diagram we understood associativity, we need, first of all we need some minimum amount of cache size. Whatever associativity you are taking, whatever the mapping you are taking as such, mapping function, it does not matter if the cache size is not enough to accommodate the current working set of model. Working set of model means the amount of data which is required, minimum data which is required to at any point of time to execute the program. And once your cache size is increasing, then the effect of these different mapping function is very less. If you have enough cache memory is there, but that will increase the cost as well. So you want to keep, your idea is you want to keep the cache memory size as minimum as possible, such that the performance should not affect it. So for that the better mapping function is required to reduce the cost as well as increasing the performance as well. So for the trade off you need the better mapping function as well as a better replacement algorithm as well. So now come to the exercise. There are two exercises planned for this lecture. One is you have a fully associative cache memory having 4 lines are there, and the main memory reference generated by the processor, these you can understand is a block addresses, basically word address that belongs to these blocks. Okay. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, these are in this sequence the addresses are generated. You have to show the final cache entries assuming the LRU is the replacement policy. So what you have to do exactly, 4 lines are there, and as per the fully associative mapping any data can go, any block can go to the any line. So line addresses you can say 0, 1, 0, 1, 1. So I am putting few references in the cache memory and giving hint to solve it. So let us say first 0 reference will come here as per the because it's a first line, because associative there is no line to block mapping is not fixed. So this first line is free. So let's say I put it 0 here, 1 next line, 2 next line, 3 next line. So far I don't have to remove anything. After that 4 is excess. Now what is the least recently used? This 0 was least recently used. So in place of 0 I will put 4, and like that you can fill the other entries and find out the final data. I hope you can do it. Second exercise is, you have a 4-way set associative cache is a block size of 16 words, 16-bit word, 4 words of 16-bit, total 4 words 16-bit, that is the block size. So you can say is a 4 words and word size is 16-bit, and the cache can accommodate a total of 4k such words. So this is the data capacity of the cache, and the main memory size is 128k words are there. How the processor address is interpreted? So from the main memory you can identify the total number of bits. So let me give a hint. 128k means 2 power 17 words total, and memory is a word addressable, let's say. So in that case 17 is the word size, sorry, address size. Now you have to find 4-way set associative, so 3 split up will be there. One is tag, one is set, and one is word offset. Is a set associativity, 4-way set associativity, the number of lines in the cache you have to calculate, and then you have to divide into the sets, how many sets are there, and then identify the number of set bits in the address, and the remaining bit will work as a tag. So let us summarize what things we discussed in today's lecture. I talked about the cache to main memory mapping. 2 mappings we discussed with examples, fully associative and set associativity, and then the cache replacement algorithms, least recently used, first in first out, least frequently used, and the random. So thank you very much, have a nice day.